Okay, welcome to the P2 revision one. Now this one was all about energy in the home, so it's a lot of generating electricity and so forth. So the first thing we looked at here was photocells. Now photocells generate direct current electricity from the sun directly. Okay, now our photocells themselves are made of this substance called silicon, and it is a semiconductor. And the way it actually works is that as that light energy from the sun shines onto our photocell, the silicon atoms absorb the energy and we release electrons from them. Now at this point, the electrons are free to flow around the circuit, and that obviously generates our electric current. So there are three things that actually determine how much current and power output we get. So the first one is the surface area of our photocell. Obviously a greater surface area will lead to greater power output. Second one is the intensity of the light. Again, a greater intensity leads to greater outputs. And finally, the distance from the light source. So the closer to the light source it actually is, the greater the power output will be. So in terms of the pros and cons of our photocells then, first of all, the pros towards them. Number one is that they have no moving parts, which means they're quite low maintenance. Second one is they don't have power cables or the need for a fuel in them, and it is renewable. As long as that sun is shining, we will have electricity. The downside, however, is exactly that. If we have no sunlight, we get no power. So if it's night time, we're not going to be able to generate electricity. If it's a particularly cloudy day, we're only going to generate very small amounts of electricity. So there is a direct link between no sunlight and having no power. So the next bit we looked at were these things called curved mirrors. Now the whole idea behind these curved mirrors is that they're going to focus the sun's light and heat on one particular spot. So what we can actually do is, if we use just a single curved mirror, we can actually use it as what's called a solar oven. So as the light and heat from the sun shine onto our curved mirror, it's going to reflect all of that back onto one particular point. And if we have a little can hanging there, then we can actually use it for cooking. If, however, we want to think about this on a much larger scale, then we can use these large curved mirrors, or a number of them, to generate steam in order to produce electricity. So what we'll find in that instance is we can make those far more efficient as a way of generating our steam if we have the mirrors tracking the sun. Because if you think about it, the sun is going to move across the sky, and if those mirrors were in a fixed position, there will only be one point in the day where they're able to work at their optimum rate. So if we then have them on this movable system, then literally they can follow the path of the sun and therefore have a much better efficiency. Now the idea of passive solar heating is literally relying on the design of buildings. So if we place windows in certain areas, we will allow heat and light in, which can then be absorbed by objects within the room. Now what we'll actually find here is that those short wavelengths are going to pass through the glass, but the longer wavelengths will be reflected, things like a red here. Now obviously we can utilise that idea in order to actually create a warmer space within our house without the need to put any energy into the system. So that's why it's passive. Now what we have is one idea, which is the solar water heater here. And what we've actually got is a glass surface on the top. Now because that's transparent, that's going to allow light and heat to pass through it. Underneath that glass surface, what we have is this network of black pipes. Now the whole idea of having them black is so that they absorb more radiation, and inside those pipes we find there is water. So as the black pipes absorb the radiation, then it's going to heat the water up inside. Again, this is a completely passive system. We're not putting any energy into it in terms of electricity to make it happen. So another way we can actually generate our electricity then is through the use of these wind turbines. So what we actually have, the wind itself is caused by convection currents on the earth, okay? So they're generated by the heating of our atmosphere, and then we get wind as a result of that. Now what our wind turbine is going to do is it's going to take that kinetic energy from the wind and change it into electrical energy. So again, we'll consider the pros and cons of this. In terms of the positive side, it's cheap and it's reliable, okay? And just like our solar then, we don't have any polluting waste being produced. And once more, this is a renewable energy source. It's not going to run out. As long as we have wind, we will have electricity. However, the downsides to it is, if we have a look in terms of the amount of energy we can generate, we would need 1,500 turbines to give us the same amount of electrical energy as one coal-burning power station. So obviously, we do have this very large requirement for space. The other one we've got is obviously some people may not particularly like the look of them, so you have that kind of visual pollution, and also as they're turning, they're not the quietest thing in the world, so there is noise pollution there too. If there's a day where we don't have much wind, our turbine isn't going to turn as much, so we're not going to make as much electrical energy either. So we do need to consider our location. A lot of these wind turbines now are being put either right along the coastline or even out at sea, because what we get there is a much greater amount of wind. Whereas if we were to put them in the middle of a valley, for example, you wouldn't find much wind, okay? So location is important. The only other side to it is it's very expensive to set these up in the first instance, so there is that cost element to them as well. Now, in terms of producing electricity, what we find is that power stations all work in a very similar manner to one another. So the first thing that's going to happen is we're going to burn a fuel. That will generate heat to change water into steam. Now, once we've got our steam, that's going to drive turbines. Turbines in turn will turn the generators, and the generators make electricity through this process called electromagnetic induction. Now, what we'll actually find is that our current is going to swap direction every half turn of the generator, which means we're making this alternating current. Okay, so AC is an alternating current, and the whole reason it's alternating is because our current swaps direction. Now, what we will then do, once we've generated our electricity, is we need to transport it from our power station to the homes and industry. And we do that via that network of cables and pylons, which is referred to as the national grid. So the dynamo effect then, this is where we've got electromagnetic induction occurring. Now, electromagnetic induction is the creation of voltage in a wire which is experiencing a change in magnetic field. So basically we're changing kinetic energy to electrical energy in this instance. Now we'll get our electromagnetic induction happening when a coil of wire is moving, hence kinetic energy, through a magnetic field. Now that will generate our electrical energy. We can also see this happening when the magnetic field for an electrical conductor changes. So that could be that the magnetic field is getting bigger, it's getting smaller, or it's reversing. So again, we will generate electrical energy as a result. Now, one thing to note though is that if the direction of movement is reversed, then our voltage and current will be reversed too. So do bear that one in mind. So if we want to increase our voltage and current, then there are three possible ways that we could bring this about. First one is to use a more powerful magnet. Second one is we can increase the number of turns on the coil, or the third one is we can just increase the speed at which our object is moving. So any of those three will increase our voltage and our current, and therefore mean that we are generating a greater amount of electricity. Now, transformers are very important in terms of our national grid, because what we'll actually find is we have two types of transformer involved in it. We've got our step-up transformer, and that one is going to increase our voltage to 400,000 volts. So these occur just outside the power station and before it goes up into the cables of our national grid. Now, it will actually transmit our electricity at that 400,000 volts, which is why those cables are so dangerous. The whole purpose of doing this is to minimize the amount of loss that we experience due to heat as our electricity is being transmitted from one place to another. But obviously when we get to the other end, when we get towards our homes and our industries, we need to make sure that the voltage is safe for people, or safer anyway. So what we see at that point is a step-down transformer, and they decrease the voltage to the safe, usable levels for our homes. Key point to note here is that a transformer will only work with an alternating current. It will not work with a direct current. Quick overview on our fossil fuels once more. Hopefully nothing too revolutionary here for you. Couple of pros for you first of all. First one, they're readily available. There are plenty still out there, particularly of ones like coal. And the second one is they do have a nice high energy output per kilogram of fuel. Downsides though, there are a few significant ones here. First one being that we're going to be generating some of those harmful emissions. So sulfur dioxide, nitrogen oxides, those are going to lead to our acid rain, whereas when we're emitting carbon dioxide, that is a greenhouse gas which is going to lead to the greenhouse effect and therefore climate change. The other sides to it, obviously it is a non-renewable energy source, which means it will eventually run out, some sooner than others. And another downside there is the fact that we do have to buy some of them from other countries, particularly oil here. Now that does mean we are reliant on other countries for a certain proportion of our fuel requirements. And that's obviously a big risk when those countries are not necessarily politically stable. So an alternative type of fuel we can use is biomass. Now this is a fuel that's going to come from either plants or animals, so it's kind of living things. So two advantages. First one is it's a renewable source. Once you've used the plant, you can always plant more. And it's carbon neutral. So just as we said before, it takes in the same amount of carbon dioxide as will later be released through burning. Downsides though, it does take a large amount of space to be able to grow that amount of plant. And we will need an awful lot of biomass to be able to replace coal, because its energy output per kilogram is lower than that of coal. So energy efficiency then, this is where we're actually going to be working out how efficient one of our products actually is. So first thing to note is our total energy input we can actually work out by just adding our useful energy output to our wasted energy output. Sometimes they ask you to calculate that in the question. They won't necessarily say we start with 100 joules of energy. They might say 75 joules is given out as heat, 25 joules is given out as light, and then ask you to calculate the efficiency. So just remember to work out our total energy input is the same as all of the outputs added together. Now to work out efficiency, all we're going to do is take the useful energy output, divide it by the total energy input, and then because our efficiency is always given as a percentage, we multiply that by 100. Now, electrical power then. When we're talking about power, we're talking about the amount of energy converted per second. So to work this out, all we're going to do using page 2 in the exam booklet once more is voltage times current. So that will give us our actual value of power in watts. Now do remember that simple little conversion. If we're talking about a kilowatt, that is the same as 1000 watts. And 1 watt is the same as 1 joule per second. So they then go on to ask you a little bit more about this, which is generally linked into the amount of money you have to spend on your energy. So first of all, if we're talking about a kilowatt hour, we're referring to the amount of electrical energy converted by a 1 kilowatt appliance being left on for 1 hour. Now that might also be referred to as a unit. Okay? So if we wanted to work out the amount of energy supplied in kilowatt hours, we would do our power in kilowatts and times it by the time in hours. Do go careful with the units there, you might have to do a conversion. Then once you've actually got the energy supplied in kilowatt hours, all we need to do to work out how much that costs is multiply it by the price per unit. Okay, so do go carefully because that would be a nice simple two-stage calculation on your exam paper. Again, you will find those calculations on page 2. Just work through it logically and take each stage one at a time. Now, off-peak electricity is sometimes cheaper if you're on the right actual energy tariff. Doesn't apply to everyone. Now, this is actually going to be working for people who have these storage heaters in their properties. So what actually happens with a storage heater is that they actually use energy at night where it's off-peak and therefore cheaper, and then they release the heat through the day when they're no longer needing to draw that electricity into them. So it's a way of heating your house without having to pay the higher price in the day. Now, in terms of the advantages here of using off-peak electricity, first thing is it's quite cost-effective for the electricity company because it means they can sort of regulate the amount of electricity they're producing and keep it at a more stable level, rather than having lots of peaks and dips it helps to regulate it over a longer period of time. The other one is obviously, as a consumer, it's going to be cheaper energy bills for us. In terms of the disadvantages, there is a slight increase in the risk of fire. Any electrical appliance left unattended is going to be a slight increase in the fire risk. And the other one is we might have to change our routine to fit around our cheap rate hours. If, for example, our electricity is cheaper at 3 AM, you might have to put your washing on at 3 AM. So obviously there is that change in routine needed in order to get that cheaper rate. So the greenhouse effect, we've mentioned it several times already. What actually happens is the Earth itself is going to absorb that short wavelength electromagnetic radiation. And as it does so, that warms the Earth up. Now, what we then see is sun radiation, which will be this long wavelength infrared, that's going to be emitted back into space. Now, that's the natural cooling of our Earth. So what we see is normally there's that nice balance between the absorbing of the short wavelength, keeping us warm, and the long wavelength being emitted back into space to cool us down. The downside comes when we build up these greenhouse gases. It's carbon dioxide, methane, water vapor. All of those greenhouse gases absorb infrared radiation. So what we actually see happening here is those gases then re-radiate heat back down to the Earth, warming us up. So it's acting like a blanket around the Earth, preventing that radiation that would have been lost back into space from actually being lost. So it keeps the Earth warmer. So our greenhouse gases. First one, carbon dioxide. Generally we get this from burning fossil fuels, and we burn a lot in the world today. The other side is that we're not removing as much carbon dioxide from the atmosphere as we used to because we've cut down a lot of trees, which means less photosynthesis is taking place. Other sources of our carbon dioxide is respiration, which is obviously carried out by every living thing, and also volcanic eruptions. Our second greenhouse gas, methane then, this is going to come from cattle. Okay, cattle create a lot of methane. We also find it from landfills because as that waste decays, methane is released. We'll also get another amount coming from our volcanoes, wetlands, and of course wild animals too. The only other greenhouse gas we need to consider is the water vapor. So this is going to be generated by oceans, seas, rivers and lakes as they evaporate, and also our power stations release quite a large amount of water vapor as well. So climate change then. Two human causes first of all. Obviously as we're burning all these fossil fuels, we're increasing the amount of carbon dioxide, which as we've already seen leads to the greenhouse effect. Another human interaction is that we're generating a lot of soot and gas from our factories, and that reflects the heat back onto the cities, making them warmer. Now in terms of the natural causes of climate change, first one is our volcanoes. As they erupt, they generate a lot of ash and gas, and that is going to reflect the sun's radiation into space. That means the Earth is going to get cooler. The other one that we could see is orbit changes, which can lead to ice ages. So the next part of this topic was about radiation. So first of all, when we've got an unstable nuclei that is decaying, it gives off radiation. Three forms you need to remember. First one, alpha radiation. This is our big, heavy, slow-moving radiation. It's basically made up of 2 protons and 2 neutrons. It's a helium nucleus. Now, because it's big, heavy and slow-moving, it's stopped very easily. So a piece of paper or your skin, for example, will stop alpha radiation. The downside to it is it's very strongly ionizing. So that means it's likely to cause damage. Our second type, our beta radiation, this is a fast-moving electron. Now, to stop beta radiation, we need a few millimeters of aluminium or similar metal. Now, it's moderately ionizing here. It's not as strongly ionizing as our alpha radiation, but it's better than our third type. Now, the third type is our gamma radiation. Now, this one, it's gamma rays. It doesn't have a mass and it doesn't have a charge. It's pure energy. Now, because of that, we find our gamma radiation is able to penetrate a long way through substances. And the only way we can stop it is by having very thick concrete or thick lead in front of it. But it is weakly ionizing in this instance. So what we're actually talking about here, all this time I've mentioned this word ionizing. What I'm talking about is that as this radiation comes into contact with atoms, it causes them to either gain or lose electrons and therefore become an ion, a charged particle. Now, if this is happening to cells in the body, then it damages the DNA, which leads to mutations, and in most cases, it leads to the cancers. So in terms of what we use radiation for then, let's think about our alpha radiation first of all. This is used in smoke detectors. So what we have inside our smoke detector is a weak alpha source. Now, as long as that smoke detector is perfectly clear, not in the presence of any smoke, then our alpha radiation is going to ionize the air around it. As long as the air is ionized, we have charged particles, therefore we generate a current which flows between the electrodes in the alarm and keeps it quiet. If we have a fire, however, the smoke that's produced as a result of that is going to absorb the radiation. So that means it's no longer able to ionize the air. So at that point, what we see is our current then stops, and this then triggers the alarm sounding. For the beta radiation then, we have two important uses here to consider. First of all is when we're making things like paper, we can use beta radiation as a thickness gauge. So what we actually have is our beta radiation source above our paper and a detector underneath the product. So what then happens is, obviously, our detector is picking up a set amount of radiation from our source as it passes through the paper. Now remember what we looked at is that beta radiation isn't great at penetrating very thick things. So what we can actually do is, as some of that radiation is being blocked by the paper as it gets thicker, then less radiation is detected underneath, which means it then sends a little message through a computer system saying the rollers need to be pushed closer together to make the paper thinner. If we have too much radiation being detected on the other side, then we send the information to move the rollers further apart to make the paper thicker. So we've set up this feedback system that is going to keep that paper at a set thickness throughout. The second use for our beta radiation is in this thing called a tracer. So this is used in medicine particularly, whereby you are given one of these beta radiation sources to either swallow, inhale, or it's injected into your body. What we can then do is use a detector and we can follow it as it travels around the body. So this allows us to obviously monitor how different parts of the body are actually working without any form of invasive surgery. So we can see if there's a blockage in the intestines when you've swallowed one of these tracers just by following it through the intestines. Obviously where there's a build-up of radiation and nothing on the other side, we've got a blockage. So it allows us to get a lot of information, again without the risk for any kind of surgery. Last one then, our gamma radiation. This one is primarily used as cancer treatment. So what we actually do here is we use a very high dose of our gamma radiation to kill those cells that are suffering from cancer. Now the key thing to remember here is that should that high dose of gamma radiation hit healthy cells, it's going to kill them as well. So what we need to do is direct that beam at the cancer cells themselves, but move it around the body. That means that the healthy cells surrounding the tumour will get a much lower dose, whereas the actual tumour itself gets a high dose to kill it off. So it does require a fair amount of control there. The second use for our gamma radiation is in terms of sterilizing things. Now, when we expose objects to gamma radiation, we're going to kill all microbes present. So if we think about hospitals once more, a lot of the bits that are used in surgery and so on are made of plastic. Now, we can't heat them up to high temperatures to kill those microbes, so instead we use gamma radiation to kill the microbes and therefore prevent infections in people. So the planets in our solar system and stars was the last bit of this topic. Now, you should remember the order of our planets in the solar system first of all. So Mercury, Venus, Earth and Mars, those make up our inner planets. Between Mars and Jupiter we find the asteroid belt, and then our outer planets, Jupiter, Saturn, Uranus and Neptune. Now, when we actually look at our planets and how they travel around the Sun, what we see is they've got this elliptical orbit. Now, the reason that they follow this same path all the time around the Sun is because of gravity. So a couple of little points for note about gravity first of all is that the further away objects are, the weaker the pull of gravity is, and the smaller objects are, the weaker the pull of gravity. Now what we actually see in terms of our planets is there is that force of gravity acting not only between the planet and the sun, but also between all the other planets within our solar system. So it's all set up in this very delicate little balancing act that keeps everything in its perfect orbits. Now the other bit to note there is the centripetal force then is a circular motion which is caused by a force which is pulling towards the centre of a circle. Okay, so just remember that definition. So asteroids and comets then. If we think about the asteroid belt first of all, the idea behind this is that Jupiter is a very large planet with quite a large gravitational attraction. Now, the theory is that that large gravitational attraction actually prevented those rocks in our asteroid belt from forming a planet during the formation of our solar system. So what we actually have is a whole belt of all these different lumps of rock that usually stay in their orbit. Now, occasionally they will get pulled out of orbit or pushed into different ones as a result of perhaps something coming in and colliding. Now, that's when obviously they can go out and strike other planets and so forth. In terms of our comets then, these are made up of balls of rock, ice and dust, and they orbit the sun in this elongated ellipse. So what happens is they travel very long distances way out into space, and that then means that they're going to be getting very cold and therefore we generate that ice. As it then comes around close to the sun on its orbit, then we get that heat, it melts the ice, and that's what gives our comet its very distinctive tail. So what you see in that tail then is the ice that's melting and bits of dust being released from it. And what we will see is as our comet gets closer to the sun, the gravitational pull is going to increase, and that makes our comet speed up. If we think about meteorites then, when we're talking about a meteor first of all, they are rocks or dust that enters Earth's atmosphere, okay? Now normally they're small enough to burn up before impact, so that's what you see with shooting stars. It's a meteorite that's burning up in Earth's atmosphere. The downside comes if they actually are big enough to not be fully burnt up by our atmosphere and they strike the surface of the Earth. So at that point what we'll see are fires developing. We're going to get hot rocks and dust being thrown up into our atmosphere. We're going to see massive craters potentially forming. Now what we can see happening is if this actual meteor is large enough, then the amount of dust and smoke that are generated can lead to climate change because it could block the sunlight from the surface of the Earth. We do have proof on Earth for several impacts in Earth's history. So those bits of proof are, we will find unusual elements in the rocks around those craters, and then there will also be a very sudden change in fossil numbers. Like what we saw with our dinosaurs, there was a very sudden change in fossil numbers which suggests that there was an asteroid impact. Now this phrase NEO, okay, just stands for Near Earth Object. So basically these are asteroids or comets that may collide with the Earth. So the whole idea here is that we've got these very powerful telescopes and satellites that are searching all of space and monitoring any of these NEOs that we've found. Obviously it's not going to be perfect. Space is very big, we don't have that many telescopes and satellites. But the theory being that we could identify any of these near-Earth objects, track their path, and then hopefully deal with them before they actually made an impact with the Earth in the future. If we consider the history of bits of our solar system, one of the more important ones we need to understand is the formation of our moon. Now, basically, the best theory that we've got at the moment is that another planet collided with Earth in the distant past. Now, as that happened, what we saw were those two dense cores of iron merged together to make our Earth's core, because as we know today, Earth's core is made of iron. All of that less dense material then was ejected out as this hot dust from the rocks as a result of that impact, and eventually they were pulled together to form the moon. Now we do have some evidence for this theory, okay? The first bit of evidence there is that the moon does have a lower density than the Earth, and it has no iron core. So this obviously supports the idea that the dense iron cores merged and became Earth's core, and all that less dense material then became the moon. The other one that we've got is that when we look at moon rocks, so when we brought back rocks from the moon on these various space missions, then they contain very few substances which evaporate at low temperatures. Okay? That suggests that the rest had boiled away at that point of impact, because remember, when these collisions happen, we generate a large amount of heat. Now, if we consider the universe, then we are in the Milky Way galaxy, and our universe is made up of over 1 billion galaxies, so it's massive. Now, because it's so big, we actually use distances in terms of light years. Now, a light year is the distance that light will travel in 1 year, so we're talking about huge distances here. Now, black holes then, what we actually find is there are points in our universe where the gravitational forces are actually so strong that nothing can escape, not even light. So what we actually see, a black hole then, has a very large mass, but a very small volume, and therefore a very high density. Now, we can't obviously see them directly. The way we actually detect them is by using X-rays being emitted by hot gases. So as those other stars emit these X-rays, then what we can see is we can watch them spiral into a black hole, and that gives us our evidence for their existence. So when it comes to space, obviously we like to explore. Now, we have two options available to us here. We can either do manned missions or we can do unmanned missions. Now, if we consider the manned missions first of all, it's going to need a lot of fuel. Okay, so that's going to make it heavy and it's going to make it expensive, because we need enough fuel not only to get these people out into space, but to bring them home as well. We've got to supply them with enough food, water and oxygen, as well as regulating their temperature and any of the toxic gases that are produced in order to keep them alive while they're up there as well. We've got to consider the radiation that they'll be exposed to and how we can minimize their exposure there. When you're up in space, there's also the risk of muscle wastage and loss of bone tissue, because obviously you're no longer exposed to those same forces as you are on Earth. And there is the psychological stress of being obviously up in space, quite isolated, and obviously any of those risks should something go wrong. So there are quite a few issues with manned spaceflight. In terms of our unmanned spaceflight then, obviously there's no need for food, water, oxygen, temperature regulation, toxic gas regulation. So because of that, it's cheaper and it's safer. Okay, there's no one that's going to die in this mission. The downsides to it though is that probe, once it's out there, it's not thinking for itself, and we can't carry out any maintenance or repairs on it. If something goes wrong, that's it, it's blown it. Okay, whereas if we had people up there, if something went wrong, then there's a chance they could potentially fix it. In terms of the origin of our universe then, we do know that our universe is constantly expanding. Now, we've got evidence from this from what's called the redshift of light. So if we look at light from distant galaxies, what we actually see is it's been shifted towards the red end of the spectrum, hence the term redshift. Now, what we can see is that the further away, then the greater the redshift. So we know that those galaxies that are further away from us are moving away from us at a faster rate. Second bit of evidence for the origin of our universe then being the Big Bang is microwave radiation. Now that occurs in all directions, and it's called cosmic background radiation. So this would have actually been caused because as our universe expanded and cools, then that background radiation cools and it drops in frequency. So again, we can use this to provide evidence for the theory that at one point our universe originated in this central point before exploding out in this Big Bang approximately 14 billion years ago. So we need to understand the life cycle of stars. Now, all stars start off with the same little series of events. First thing is our star is going to form from clouds of dust and gas. Now, gravity is going to pull all of that together to make what's called a protostar. So what we then see there is our gravitational energy is going to be converted into heat energy. Now, when our protostar gets hot enough, then what we see happening is those hydrogen nuclei start to fuse together, to make helium nuclei. As that happens, we give off lots of heat and lots of light. And at this point that this is happening, that's called a main sequence star. So this is basically where our sun is at the moment. It's a main sequence star. We've got hydrogen nuclei fusing to make helium nuclei while giving off large amounts of heat and light. As that hydrogen begins to run out, then our star is going to swell up and become this thing called a red giant. Now what happens next in the life cycle of a star depends on the size of it. If we consider small stars first of all, then after they've become a red giant, they're going to eject dust and gas to form a new planetary nebula. What's going to be left behind then is this hot, dense, solid core, which is going to make up what's called a white dwarf. Now that white dwarf is going to cool down and eventually it just fades away. If we look at a large star, so these big stars that we have, from the red giant, it then becomes this thing called a red supergiant. And at this point it's pulsing. It's expanding and contracting several times until eventually it explodes out into this supernova. And at that point we throw out dust and gas back into space and we leave behind this very dense core, which is a neutron star. Now if our original star was big enough, then that neutron star will eventually become a black hole. So the last part of P2 is all about basically the history of our universe and the theories around it. So it's a bit of history here. So we'll start off with the ancient Greeks and a guy called Ptolemy. Now his theory was that the sun, the moon and the other planets orbited the Earth. So that's called the geocentric model. Basically Earth was smack bang in the middle, everything else orbited us. That was the original idea there. Now, a bit later on, we had this guy called Copernicus come along, and his idea was that the sun was at the centre, and all planets orbit around the sun. So he suggested this, but he didn't really have any evidence for it, so it was very hard for him to actually have people believe his theory. It wasn't until the time of Galileo that we got a lot of evidence for the Copernican model. The first thing that Galileo did was he was able to observe Jupiter's moons orbiting around it. So that obviously provided the idea about orbiting around objects. The other bit that he observed was that Venus had phases based on its position to the sun, again suggesting that Venus went around the sun and not around the Earth. So what we actually see, as with a lot of scientific theories, is it takes a long time for them to actually become accepted, because we need to provide proof, and it's not always available at the time of the theory's incarnation. So obviously we need to think about when these theories come into their existence. It might be a long time before it's believed, particularly if it's going against religious beliefs. So that sums up all of P2, and again, if you have questions, make sure you ask prior to the exam.